morning, everybody. Hope you're all healthy and safe at home. We are going to continue with our section 9.9, Independence of the Path. So in the previous lecture, we had seen the fundamental theorem of line integral, and we have proved that if the vector field given to us was conservative, then line integral of C f dot dr, it is path independent, that is, it does not depend on the path. So in this lecture, we are going to discuss about another theorem, theorem 9.9.2. The theorem states that in an open connected region R, integral over C f dot dr is independent of the path C if and only if the vector field f is conservative in R. So this theorem is a if and only if statement, that is, both of the things are true. That is, if the integral is path independent, then the vector field f is conservative, and conversely, if f is conservative, then the integral over C f dot dr is independent of the path. Now, the first part, we have already seen in previous theorem or in the fundamental theorem that we had proved that if f is conservative, if the field f is conservative, then we had proved that integral over C f dot dr, the line integral, is path independent, right? So we don't need to prove this part again. I hope you guys are clear with the proof which was done in the previous class. Right? Now, what we are going to do is we are going to do the converse part. That is, we are going to assume that integral over C f dot dr is path independent. Okay, and we are going to prove that it is this f is conservative. So let us see how we can prove it. First of all, what we are going to do is we are going to consider a connected region R. Consider a connected region R, and let C be a curve and let us consider 2 points in the curve, say x dot, y dot, and xy. Okay, let these be 2 points on the curve C. Okay, now let us see a figure of the region that we are going to consider. It is like a random figure. That is, we are having the region R and we are having a curve C. Okay, this is our curve and we are considering this point to be x dot, y dot, and this point is x, y. Alright, now what we are going to do is we are going to define a function, define phi of x comma y, phi of xy is equal to integral x dot, y dot to xy f dot dr. Okay, now here where f is of the form, f is equal to p of x comma yi, we have defined this in the previous sections and all, plus q of x comma y j. Okay, now what we are going to do is we are going to choose a point, choose any point, say x1, y, such that x1 is not equal to x. You just have to keep this in mind, that is, x1 is not equal to x, such that there is a condition. What is the condition of choosing this point? The line segment joining these points, joining the point x dot y dot and x1y lies inside R itself, inside the region that we have chosen. So let us just draw a figure which will make the idea a bit more clear. This is the region that we had considered before, and our point is chosen in such a manner that the line segment joining these points lies inside R itself. So this is our x dot y dot, and this is the point x1 y, and this was our point xy. So we have to choose this point in such a manner that the line segment joining x1 y and xy lies inside R itself. Now we had said that the integral is path independent. So we had defined phi of xy to be integral f dot dr. So it does not depend on the path. So we can split the integral into two. That is, this is integral x dot y dot to x1y f dot dr plus integral from x1y to xy f dot dr. Now what we are going to do is just I want you guys to recall one more thing. We had seen that f dot dr is nothing but p of xy dx plus q of xy dy, right? Dr was dxi plus dyj, and f is pi plus qj, so the dot product will be p of x comma y dx plus q of x comma y dy. Now what we are going to do is we are going to partially differentiate this function phi. Phi is a function of x and y, so we are going to partially differentiate this with respect to x. That is dou phi by dou x. What will the value be? Now let us take both the terms separately. If you consider the first term, integral of f dot dr, let it be whatever value which we get, and we are applying the limiting condition from, or the limits are x dot y dot to x1 comma y. If you see x dot and x1, these are all a particular value, so they are not dependent on x. Okay, so in this integral we will not have any term corresponding to x. There is a possibility of having a term with respect to y, but no term with respect to x, because we don't have x in the integral. So what will be the differential of this? That is, when we are partially differentiating phi with respect to x, we have to differentiate the term with respect to x, keeping y as a constant. So here there is no term of x, and there is a possibility that there is a term of y. So what will be the value? The integral will be 0. Sorry, not integral, the differential will be 0. Why? Because there is no term of x in it. And now let's see the second integral. That is, we have to differentiate this integral with respect to x. That is dou by dou x of integral. So here there is a chance of having the term x, or there will be a term x, because we have to apply the limit x comma y. And now let's write f dot dr as p of xy dx plus q xy dy. Now just look at the limits that we have given. You can see that here we have x1 and here it is x, and if you see, there is no change in y. Y is remaining the same, right? So what happens is, when y is constant, what will be dy? Dy will be nothing but 0. So this term reduces to 0. So what do we get? We get dou phi by dou x is equal to dou by dou x of integral x1y to xy p of xy dx. So dou phi by dou x is dou by dou x integral of something dx. So using fundamental theorem of calculus, we get this value to be dou phi by dou x is nothing but p of x comma y, using the antiderivative concept of fundamental theorem of calculus. Now similarly, we can obtain the value of dou phi by dou y, right? Again, dou phi by dou y. What do we get here? We will get it is equal to q of x y, right? Now, what is gradient of phi? Gradient of phi is nothing but dou phi by dou x I plus dou phi by dou y j. Now what was dou phi by dou x? This is p of x y I plus q of x comma y j. Now what was our considered value of f? It was the same, right? We had considered that f was p of x y I plus q of x comma y j. So we get gradient phi is equal to f. So what is meant by this? This is meaning that f is the gradient of some scalar function, which implies f is conservative, right? That was the definition of conservative vector field. So I hope the proof is clear for you guys. It is a simple proof. We just had to consider the fact that the path of the integral is independent, and that prove the theorem by taking the partial derivative of the function phi. So we will stop for now. That's it for today's section. Thank you. Stay home and stay safe.